Well, hello. I thought it useful to illustrate the meaning as per the Tesla record, the model-based definition of the datum collection. Okay, so this is what's intended according, just reading the drawing as per the standard. Okay, so we have three datum targets in here. Those are the A targets. Okay, and they're defined, by three surfaces, which I'm highlighting here in blue. 1, 2, and 3. The first two are, this one is A1, there's A2, okay, and this would be A3. And if we look at it from the side, okay, we can see that there is an offset between them. Okay, so A3 is lower by 3 millimeters, okay, but all these surfaces are parallel to one another. Okay, so it really doesn't matter whether you choose, in this case, as this to be the datum axis A or this one, because they're just 5 millimeters apart basic. So it's really material, although it would have been nice, for the drawing to contain a specific chosen plane, if you will. Okay. Then are the B datum targets. Okay, they're defined by this surface and this surface. Okay. Now those are at a basic 85-degree angle instead of a 90. Okay, and that doesn't pose a problem at all, and you'll see how those planes are formed here in a little bit. And then finally, we have this this block whose distance between the two sides, okay, the midplane of those two represent datum C. Now, datum C is usually utilized in the drawing at its maximum material boundary. Okay, so it means that it's going to be that the width is going to be defined at the virtual condition, and that virtual condition works out to be 12.85 millimeters. And that 12.85 comes from the 13 nominal minus 0.05 of size tolerance, and then a 0.1 of millimeter positional tolerance relative to A and B, which is really an orientation allowance. So the combination of the position and the size tolerance at maximum material condition yields 12.85 as the virtual condition. Okay? And this would be 12.85 with the midplane being perfectly orthogonal to datums A and B. Okay. So again, this is the intended representation of the datums. Of course, in practice, if we had such a fixture, we would bring in the part. Okay, and now the game would be first, to rest the part on datum A. So for that, I'll turn to a side view, or what should be a side view, and this is defined as a top view in the Tesla drawing, unfortunately. Okay, and we would bring this, and we just make sure that we're making contact there in the bottom. Okay, so this is our point of concern right there. Okay, so contact there and contact here. Okay, so however the part contact, of course, we're going to have perfect contact here because I'm contacting the CAD, and the datum targets have been built, to the basic dimensions, that are embodied in the CAD. Okay. But in real life, however this part, settled on there, that would be datum A. Okay. Next order of business, would be to bring contact to datum B. And notice that, the datum B is aligned, so as to correspond, with a 13 millimeter patch there for B1 and B2. Okay. And now with A and B, then C would determine the midpoint. Okay, so and that's probably best seen here if I turn on transparency for the part. Okay, and in fact, if I look at a top view, okay, you'll see that there's a little bit of wiggle room there, and so that gap is the distance between the nominal, which is the 13 millimeter, and then the 12.85, which is the virtual condition of this gauge. Okay, so but in practice, this only allows translation along the long axis of the extrusion. And by the time all this is said and done, we have these datums. Okay, so we have datum A. Okay, so it's not bothering us. Okay, so datum A. So in this case, I have made them coincide, with the top surface. But if this of A1 and A2, but if I had used A3, well, that's just a 5 millimeter basic. Okay, so that's why I say that it's immaterial, whether datum A references, the A1 and A2 or A3. Then datum B, if I turn it on, is aligned, with this two surfaces. Okay, it's defined, by these datum targets. Okay, it is 85 degrees basic to datum A. Okay, now at their point of intersection, we have an axis. Okay, which I'll turn on, and now we can create, what I call the datum B orthogonal. Okay, so when I turn that on, this is just an orthogonal plane. Okay, so if I'll look from the side, again, this is a plane that is at 90 degrees, to datum A that passes through the point of intersection. Okay, so this would be compliant with the standard. Okay, and then finally we have datum C, which is just the midplane of the C datum target. Okay. So where these three intersect, in other words, right at this location, okay, this is where you could take measurements and compare them to CAD. This is where you could take your basic locations of all the part features and compare them to just the CAD derived locations. Okay, once you create a coordinate system in CAD at that same place. And I'm showing that right now here. Now, in this case, the x-axis, well, really the direction of the x, y, and z axis is entirely arbitrary, right? What matters is their orientation. And here you can see from the side, what that would look like. So in this case, z is pointing up and x is pointing forward.